Afternoon. Good afternoon, all of you.
Good afternoon.
Good afternoon. Devasana, Ahlam, good afternoon.
Good afternoon, ma'am.
Hello, Fisan.
Ma'am, my bag was not missing. Yeah, my book.
What?
My book was there. My book was not missing. That's
Huh? Not
Am I-
clear, Fisan.
now can hear.
Now okay.
My book was not there. My bag is there.
Go and take.
I take.
Ah. Okay, okay, children. So we are going to start our new chapter, chapter 15, probability, last chapter of this term. Okay. So you write heading chapter 15.
Same portions no that in 8th and we learned no, like that no. And same like the method no. Head and tail that.
Symbol. Probability is symbol. Very simple. Only one exercise we have. Simple chapter it is. Chapter 15, probability.
Ma'am, do we need to try this heading introduction?
No need to study. No need to write. Okay, children, listen, all of you, listen. So from our 8th standard onwards, we are studying probabilities, isn't it? The basics starts from 8th standard. 9th you have studied, and 10th also we have a small chapter, probability. 9th you have studied experimental probability or empirical probability. Experimental or empirical probability means it is based on real experiments. Experimental probabilities based on real experiment. For example, suppose we are tossing a coin. While tossing a coin, there are two outcomes. Okay, the result of an experiment. Tossing a coin is an activity, isn't it? Tossing a coin is an activity. In probability, for an activity, we will mention it as an experiment. Tossing a coin is an experiment, and each experiment has one outcome. Outcome means a result. Ahlam, what is the result of tossing a coin? What was that outcome of that experiment? Tossing a coin. While tossing a coin, what will be the outcome, Ahlam? Unmute and say. What are the outcomes? What will happen if you toss a coin? Unmute, you are not unmuting. You can't? Okay, leave it. Devasana, what are the outcomes if we toss a coin? Devasana,
Yes,
what will happen? When we toss a coin, what are the outcomes?
Our tails will.
the tail.
Head or tail, yes. So head or tail are called outcomes of an experiment called tossing a coin. Okay. So experimental probability means we are conducting an experiment and find out what is the result. Okay. So that is known as experimental our probability. Finding probability by experiments are known as experiment probability that we have studied in year 9th standard. And this year we are going to study theoretical approach. By using some formula we are finding the probability. Using formula we are finding how that formula derived. The formulae are derived with the help of these experiments. Okay. So theoretical probability or theoretical approach of probability based on the formula for finding probability. Okay. And as we know, we suppose we are tossing a coin 100 times. 100 times we toss a coin. As we increase, we know, can we predict what will come, head or tail? That we cannot predict. Okay, that's why we are saying we are using tossing for taking some decision in some games or all. We are tossing uses using this tossing a coin to take some decisions. Okay, so we cannot predict what will come if we toss a coin. But as we when we toss a coin 100 times or 1,000 times, the number of heads and number of tails will be will come very closer to each other. Okay. If we toss a coin, if I toss a coin 100 times, one second. If we toss a coin 100 times, suppose the head is there are head and tail. There are 55 head and 45 tail. Okay. So there is a difference between 45 and 55, isn't it? But as we increase number of tossing to 1,000, 10,000, lakh and 10 lakh, these numbers, number of head and number of tail seems to be approach very close. Okay, they will be going to be equal to each other. They will going to be equal to each other. But it is it is proved by experiment. It is proved by experiment from 18th century. See in the text you can see from the 18th century onwards, scientists start experimenting this result. This 18th century French naturalist Comet de Buffon tossed coin 4,040 times. 4,040 times, and he got 2,048 heads. Okay, so both are probably equal to same. Number of tails and number of heads are going to be same if we increase the number of tossing a coin. And see, Carl Pearson, very famous statistician, he tossed the coin 24,000 times and find out how many times he is getting head and getting tail. Here also he is getting 12,012 heads. See, the number of 24,000 and head is 12,012. See, the number of heads and number of tails are coming closer to each other. Sometimes they will be coming very close to each other. The difference between their numbers will be very less. Okay, so this is proven by many scientists using experiment. If we increase number of tossing by 1,000, lakh or 10 lakh times, what will happen? The number of tails and number of heads will be very close to each other. The difference between them will be very less. Okay, so that is theoretical probability. We have not theoretical, experimental probability that you have studied earlier. And this okay, and in this year we are going to study about theoretical probability based on already proved theories we are using, and we are using some formula to find out probability of an event or of an experiment. Okay, so children, you give a heading, a theoretical approach. You can give this heading, theoretical approach, right? Subheading as theoretical approach. Children, 1 second. Here it is heavy rain. I can't hear you. I will close the door and come. 1 second. Okay, children. Before moving to probability and its formula to find probability, we will recollect some terms that we are using in probability. Okay, first one is random experiment. What is random experiment? Anyone?
Random.
Experiment. Random experiment. Tossing a coin is a random experiment. Throwing a die, taking a card from a pack of playing cards. All these are random experiments, which means we don't know the result. Okay, without knowing what will happen, without knowing the result, we are doing it. Okay, taking a basket containing full of identical balls, taking a ball. It is a random experiment. Okay. And fair coin means unbiased coin. A correct coin, not an unbiased coin. Unbiased means a tendency to move to one side. Unbiased means both result have the same chance to occur. That is unbiased. Unbiased coin. And outcome. Random experiment outcome. Outcome means it is the result of the experiment. Outcome is the result of the experiment. And equally likely outcome. Equally likely.
And we will try this random experiment.
Equally. If you want, you can write equally likely outcome. Equally likely outcome. Equally likely outcome. Head and tail are equally likely, which means the possibility to occur, the chance to occur, these two head and tail are same. Okay, they have equal chance. While tossing a coin, getting a head or tail has equal chance. That is equally likely outcomes. In this chapter, we are studying all our experiments are equally likely, which means in all the experiment, the chance for getting the particular outcomes are equal. So, throwing a die, what are the outcomes? While throwing a die, what are the outcomes, Eva? What we will get when we throw a die? Eva?
2, 3, 4, 5, 6.
Numbers?
1, 2, 3.
1, 2, 3, 4, 5, 6. Throwing a die, we will get numbers from 1, 2, 3, 4, 5, 6. And getting any number, getting 3 or getting 4, getting 5, all are having same chance. Okay. So 1, 2, 3, 5, 6 are equally likely outcome. They have equal chance to occur. Getting 1 is same as the chance for getting 1 is same as chance for getting 5 also. Chance for getting 5 is same as chance for getting all other numbers 2, 3, 4 and 6. So these outcomes are called equally likely outcomes. Okay. Okay. Now we will move to our theoretical formula to find probability of an event. We have only very few formula. That is first formula, right? theoretical probability. I think you have written the heading, no? Theoretical probability, or also we can call it as classical probability. And formula is, and E is denoted as event. Event means it is a part of the experiment. But tossing a coin is an experiment, or it is an activity, and that also we can call it as event also. It is an event. Okay. And in that experiment, we have two outcomes, head and tail. These are the events of the experiment tossing a coin. Tossing a coin is an activity, or it is an experiment, and its events are getting tail or getting head. These are the outcomes are called events. Okay. The one subset, part of the outcomes are called events. Like while tossing a coin, the outcomes are head and tail. And tail is an event, head is an event. Okay. And while throwing a coin, throwing a die, the outcomes are numbers 1, 2, 3, 4, 5, 6. Getting a 6 is an event. It has happened. Chances are 1 to 6. But 6, if we got 6, 6 is an event. Okay, understood? Outcome and event. Outcome, then event. Event is the result, the final result of that experiment. Outcomes are possibilities. Head or tail are possibilities. If we get head, it is an event. Okay. So, theoretical probability for an event, write this formula. For an event E, for an event E, capital E. For an event E, probability of E is equal to number of outcomes favorable to E. The same formula we have studied from 8th onwards. Okay. Number of outcomes favorable to E divided by the number of all possible outcomes of the experiment. Total possible outcomes. The number of all possible outcomes of the experiment. Outcomes of the experiment. Probability event E is okay, children, all of you write 2 times this formula now itself. Write 2 times.
No, can you show the board?
Hmm?
Can you
You
show
want
the
to
board?
see? Wrote all of you?
1 minute. I'm finished.
Okay. Okay, now we will do some examples. Okay, all of you listen to the board. First example, we will consider tossing a coin. Hmm? Tossing a coin. Okay, while tossing a coin, outcomes are what?
Head and tails.
Outcomes are head and tail. Hmm? We have two outcomes, total two outcomes. Total outcomes are two. Head or tail. Head or tail are the outcomes. Now, probability of getting head. Probability of getting head, we can write P of H. Probability of getting head, P of H is equal to, by our theoretical probability, by the formula, what the number of outcomes favorable to a particular event. Here the event is H. Here the event is H, isn't it? Here event is head. Okay, so tossing a coin, probability of getting head equal to number of outcomes favorable to H. How many H will be there when we toss a coin? How many H can come? How many H while tossing a coin? How many H's? How many heads will come when we toss a coin?
1, 2.
Two heads will come when we toss a coin.
One head.
1, 1, 1.
One head.
Only one. So probability of getting head equal to, by our formula, what is the formula? Probability of an event equal to number of outcomes favorable to the event. So number of outcome favorable to head. How many heads will be there? Only one head. 1 divided by total outcomes. When we toss a coin, what are the total outcomes?
2.
2, 1 by 2. Okay. So similarly, probability of getting tail, P of T also equal to number of outcomes favorable to getting head, getting tail. Number of outcomes favorable to getting tail is, how many are there? How many tails will be there when we toss a coin? 1 and
1, 1.
total 2. So probability of head equal to probability of tail equal to 2. Probability of head equal to probability of tail equal to 2. Similarly, are you writing this?
Yes, ma'am.
Right? Over?
1 minute, 1 minute.
No. Because this very simple. We have already studied from 8th, isn't it?
I'm finished.
Now we will consider next example, example 2, throwing a die. Throwing a die. Okay. So outcomes are 1, 2, 3, 4, 5, 6. These are the outcomes if we throw a die. These are the possible outcomes. The total number of outcomes are 6. Total number of outcomes 6. Total number of outcomes 6. So probability of getting number 5. That is probability of 5 will be what? How many 5s? The probability of an event equal to number of outcomes favorable to that event. Here getting 5 is an event. Here the event is getting 5 is the event. Here our event is getting 5. So how many numbers are favorable to getting 5? How many 5s will come? If we throw a die, how many 5s will come if we throw a die? Angelo, how many 5s we will get if we throw a die? Suppose 3. Suppose did you know what is a die, Angelo?
No.
Did you know what is a die?
Yes, ma'am.
Yes. So suppose you are throwing a die. How many 5s will come if you throw? How many chances are there for getting 5? 6. All sides are 5 in your die?
No, ma'am.
Wait, Susan. Angelo. Suppose you are throwing a die. You will get 6 5s. If any face come, it is 6. It is 5.
No.
How many 5s are there in your die?
1.
1. Yes, only 1 is the possibility of getting 5. The favorable event, the number of chances favorable to 5. Number of chances favorable to 5 is only 1. Only 1 5 will come. Okay, only 1 5. So probability of 5 will be 1 divided by total chances. Total chances 6. Total chances 6. So probability of getting number 5 is 1 by 6. Similarly, what will be probability of getting 3? Probability of getting 3 shown
1 by 6.
1 by 6 because only 1 3 on a die we have only 1 3. So outcomes favorable to 3 is only 1. Okay, there are 6 chances but only 1 3. So 1 by 3. Probability of getting 5, Navneet? No, getting 4. Navneet?
Ma'am, 1 by 6.
1 by 6. Okay. Now probability of getting a number less than 4. Probability of getting a number less than 4. Probability of getting a number less than 4. Raya, how many possible outcomes are there for a number less than 4? Raya, how many outcomes will come our event is we are considering number less than 4. So what are the possible outcomes? Raya, louder. Can you say loudly? I didn't hear. What did you say?
Ma'am, is it 1 by 4?
Louder, little bit louder.
Ma'am, 1 by 4.
No, I'm asking what are the possibilities? And I'm getting number less than, which are they? Number less than 4. Which are the possibilities? Say. Raya,
Yes, ma'am.
say little bit louder. I can't hear you properly. Number less than 4. What are the possibilities? Which are the numbers less than 4 on a die? Huh?
1, 2, 3.
1, 2, and 3. The possible outcomes are, possible events are possible events are 1, 2, and 3. So there are possible outcomes, 3 possible outcomes. Okay. So it is 3 divided by 6, 1 by 2. Probability of getting a number less than 4. We have 1, 2, 3, 4, 5, 6 are our possibilities, all total possibilities. In that, our event is a number less than 4. Okay, favorable to that event are 1, 2, and 3. Our considered event is getting a number less than 4. Favorable to that are 1, 2, 3. So there are 3 events favorable to the event less than 4. There are three numbers favorable to the event which is less than 4, number less than 4. So it is 3 by 6 equal to 1 by 2. Next one, probability of even number. How many even numbers, Rohan? When we throw a die, even numbers, how many are there?
4. I'm 6.
Even numbers.
Even also.
Mm. Even numbers? 2. Then
4,
4,
6,
6, 2, 4, 6. So the how many? What are the favorable
3.
outcomes? There are
3.
3 favorable outcomes divided by total outcome. Again 1 by 2. Similarly, same way we can write probability of getting an odd number. How many odd numbers? How many odd numbers?
3 by 6.
3. 3 by 6. 1 by 2. Getting a prime number.
Ma'am, 9.
Hmm?
9.
9. Prime number.
Prime number.
Primes. Only we have 6. Up to 6. We have numbers. While throwing a die, getting a prime number. Which are the prime number? First prime number is Atulya.
2.
First prime number is
2.
2. Then 2. Then
4.
4. 4 is the prime.
3.
3.
5.
Hmm?
5.
5. Any other? No. 2, 3, 5 are the prime numbers. So 3 by total is 6. That also 1 by 2. Next, probability of 7, getting 7. What is the probability of getting 7? Getting number 7. Sania, what is the probability of getting number 7?
0.
0. There is no 7 on a die, isn't it? So 0 by 6. 0. It is known as impossible event. It's known as impossible. Getting a 7, if you want, you can write that. It's an example for impossible event. Getting 7 is an impossible event. Getting 7 is an impossible event. Now, example 3. Suppose we have a basket which contains um, one blue ball and 2 yellow ball, 3 red ball. 1 blue ball, 2 yellow ball, all identical balls, color different. 2 yellow ball and 3 red balls. We mix all these balls together. Okay. Now, what will be the probability of, first of all, you write total balls. Total balls. Basket contains total number of balls. 6. There are 6 number of balls. Probability of getting a blue ball. How many chances for a blue ball? How many blue balls are there? 1. So total balls 1 by 6. Probability of getting a red ball. Red ball. How many chances are there for red ball? 3. 3. So 3 by 6. Probability of getting yellow ball? 2 by 6. Okay. Okay. Now, we have already studied probability of head equal to 1 by 2 and probability of tail also equal to 1 by 2. If we add probability of head plus probability of tail, that is 1 by 2 plus 1 by 2 is 1 by 2 plus 1 by 2 is, what is 1 by 2 plus 1 by 2?
1 man.
1 by 2 plus 1 by 2. That is, while tossing a coin, the possible outcomes are head and tail. Tossing a coin, possible outcomes are head and tail. If we add the probability of both possibilities, both outcomes, that is, we are adding probability of head and probability of tail, we will get 1. Similarly, one more example. Here we have 2 outcomes, 2 results, 2 outcomes. We add the probability of both outcomes. Sum of probabilities of all the outcomes. Here all means only 2, head and tail. Probability of head is 1 by 2. Probability of tail also 1 by 2. We will get 1. Now we will consider tossing a coin. The outcomes are 1, tossing, not throwing a die. 1, 2, 3, 4, 5, 6. Throwing a die. So, and we know that probability of 1 equal to 1 by 6. Getting 1 is 1 by 6. Probability of 2 also 1 by 6. Probability of 3 also 1 by 6. Probability of 4 1 by 6. Probability of 5 is 1 by 6. Probability of 6 also 1 by 6. These are the possible probabilities of all the outcomes of the event or the at experiment throwing a die. Now we are adding the probabilities of all possible outcomes. Probability of 3 plus, probability of 4 plus, probability of 5 plus, probability of 6 is equal to 1 by 6 plus, 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 1 by 6. And it is equal to, what? 1 by 6, 6 times. Equal to
6 by 6.
6 by 6. 6 by 6, that also 1. Which means if we add probabilities of all possible outcomes, the sum is 1. Probabilities of all possible outcomes, the sum is equal to 1. Okay. Here. So this also you write. These two, after that we have to state, we have to write a statement. Very important statement. Probability, the sum of the probabilities of the sum of the probabilities of all possible events of an experiment is equal to 1. Highlight the sentence, very important. One more questions will come from this.